Hello everyone! Are you waiting for holiday seasons as I do? Is it only because of holidays? Well, I'm not, because every year I'm waiting for the holiday season to solve Advent of Code. Did you hear about Advent of Code? Let me quickly introduce it to you. Advent of Code is an annual series of coding adventures, coding puzzles if you will, which we should solve to the best of our ability, obviously. And it actually allows us to learn a lot of things, and in my opinion, learning is one of the most interesting things in my life at all. I can learn new libraries, new algorithms, new languages, whatever. I can learn everything, and Advent of Code is an actual amazing excuse to do it. It allows me to distract from my daily job and switch to solving something untypical. Hi, my name is Pasha, and I'm solving Advent of Code for more than 5 years already. Not every year I'm able to finish it, sometimes I don't have enough time, sometimes just tasks are too complex. But this year, and starting from this year, Advent of Code is actually shorter. It's only 12 days instead of 25, which gives me some spare time during December. Actually, I would say it gives me some time with my family, which is a nice thing. And this is how my main page of Advent of Code currently looks. It means that I solved all 12 tasks and I have 24 gold stars for them. Today we'll be looking at them, and hopefully you'll learn something new for you too. Our adventure starts on day 1 with a task called Secret Entrance. The idea is we have a code block and we have a wheel on it which we should rotate right or left. Let's look at our test input, how it looks. So, for example, this means we should rotate it 68 ticks to the left. This one 60 ticks to the right. And obviously on my real input there are many lines, it's more than 200 of them, and sometimes we'll rotate our wheel more than 800 times. Our task is to count how many times will we pass 0 for the second part and how many times will we stop on 0 for the first part. The idea of the task with the second day is also quite simple. We have to look for repeated patterns in numbers. So for example, if our number is something like this, I can't count obviously, but the idea was this part of the number should be repeated 11001, something like this. How do we do it? We should cut these numbers in halves, something like this. And now we should generate all possible variations of what can be repeated. Our input is in the form of set of ranges. For example, this is set from this range from this number to this number, this set from this number to this number, from this number to this number, and so on. The way I approach the first part is very straightforward. I just calculate all the possible variations of pattern of which my number can consist and count it. The second part is slightly more interesting, but I actually reuse the same solution. Now we have to find numbers which consist of multiple repetitions of the same number. For example, 101, 101, 101, 101. It is 12 numbers, 12 digits, I should say, and we should understand how many possible lengths of patterns is possible there. Since it's 12, then it can repeat one number 12 times, or it can repeat 2 numbers 6 times, or it can repeat 3 numbers 4 times, or 4, 3, 6, 2. I think this is all. And approach I took is absolutely the same. Just I included this max repetitions allowed, and for the first part it will be 2. For the second part it will be long max value, obviously. And I still generate all possible patterns, and I check if my range contains any of the allowed numbers. Let's look at the visualization. Here it's pretty boring because it's just numbers. Will look something like this. So for part 1, for example, I have these ranges from 11 to 22. There are 2, and from 95 to 115 there is 1 entry, and so on. For part 2 it's slightly more interesting, and we have to look for a sum of these numbers. This is all we'll get. Like, for example, for this range there is 222 repeated 2 times, or 22 repeated 3 times, or 2 repeated 6 times. Or for example, for this range there is only one value, 824 repeated 3 times. And this is all for the day 2. Also, it's important to know that we start from the position 50. So here is how we solve it. Our current position will be 50, and we'll have some kind of counter. Then we'll iterate over all the strings we have. If the string starts with L, we'll change our current position. And since it can become more than 99 or less than 0, we should normalize it back, obviously. This is how we do it. And the same we do for the right. Just instead of minus, we use plus and normalize our position. And if after normalization our position is 0, we increment the counter. For the part 2, we'll do something very similar, but we will use this beautiful function floatDiff, which allows us to understand where will we stop. It divides the value by other value, flooring the result to an integer that is closer to the negative infinity. And then we normalize our thing again. Here we just increment the amount of passes. Let's launch the program real quick. Oops. And we see the result immediately. It's here. This is for real input and this is for test input. Also, thanks to Gemini, I was able to implement visualizations for almost all of the days of Advent of Code. Let me show you the visualization for the day 1. Oops. Let's open day 1, right in IDEA browser. Perfect. So here we have our wheel. Can I zoom it out? And let's load my test input and we'll run the thing automatically. And you see how it works. Here it counts how many times it landed on 0, and here it counts how many times it passed the 0. The task of day 3 is actually pretty straightforward. We have lines of digits like this, and for the part 1 we should find the best number we can find inside this one without reordering digits. For example, for this number it will be 98. For this one we'll have to pick 8 and then 9, and for this one we will have to pick 7 and 8. Since we don't need to reorder anything, we actually do a very simple thing. We should find the largest digit in the head of our list. It means we should not look at the tail, only at the head. And our tail will be how many steps do we need to make after this step. And the solution is also very simple. It's a simple tail recursion. We have this max joltage. Joltage is just a thing from Advent of Code. We have input, which is just a list of digits. We have how many steps we have to make and current sum we have. So if there are no more steps to make, then it will be our current sum. Otherwise, we count how many steps we should take and take the head of our list of digits. Then we find the index with the biggest digits there. Then we will find the index of the biggest digit, and then we'll pass execution to the next step reducing steps to make by 1, and current sum we should multiply by 10 and add our current digit, which is just grows our number slowly. And this is the whole solution. It works almost momentarily. It's 4 milliseconds. Let's look at the visualization. Here it's pretty neat. Opening it in our default browser again. Let's just, it's not that beautiful here, but probably should work. Yeah, this is how it works. And this is a very, very slow execution. As you saw, the whole thing is being solved in 4 milliseconds. The day 4 is the usual task for Cell Automata. Here is an example of our input. It's just a labyrinth where we should remove all the things, all the adds, where we don't have more than 4 another adds around. And as any Cell Automata, it's solved pretty easily. We just count them, how many of our points do not have neighbors or do not have enough neighbors. For the part 2, we should remove them one by one until we remove them all. And again, the solution is very simple. We just do the same thing in many iterations. What I like in this task, I actually like the visualization. Let's look at the visualization of my part 4. I should copy my input for that. Here is my input. It's humongous, as you can see. Let's launch it right here. And let's close this part. We'll hit load input. This is this huge field. Let's run it, and we can see that it is removing dots one by one until we know how many things we removed. And at some point it continues to delete only small portions of our field actually. Here it deletes the tail, and it continues to delete this another tail, and this is all. And this is our final solution. Day 5 is also not tricky. The idea is very simple. We have set of ranges, and for the part 1 we should count how many numbers will fall into any of these ranges. And in Kotlin it's quite trivial. We just take all the numbers, and for all the ranges we'll check if the range includes the number, and we'll output the count. Second part is slightly more interesting. We don't care about the single numbers anymore. We have to count how many integers, how many numbers all of these ranges contain. But these ranges can overlap, so we have to not count overlap twice. I did it my way. I know that other folks did it another way. What I did, I have implemented a function which will do one long range minus another long range. And obviously, if the second long range is in the middle of the first range, it will split the first range into 2. If it's in the beginning, it will just return the end of our first range. And if they don't intersect, it will return just the first range. And for the part 2, I just deduce from the first long range all the long ranges starting from second, for the second all starting from third, and so on. And then I have the list of all the non-intersecting ranges, and I just sum it and return the number. It might sound complicated, but as you can see, it's just a bunch of ifs and elses, which accounts for all the possible combinations of our ranges. And it works quite fast. It's like milliseconds again, and even for this huge number, because I don't split ranges into single numbers. And to count, to understand what's the length of my range, I should just deduce first element of the range from the last element of the range and add 1. This is all. Day 7 is actually my favorite task of the year, mostly because of the visualization, but the task itself is also beautiful. So we have this maze or something, which looks like a Christmas tree, but it obviously isn't. And we start here at the letter S, and we have downward beam from it, and beam will split on splitters, which are these marks. And for the first part, we should count how many times the beam will be split. And for the second part, we should count how many beams are there, because sometimes beams intersect. What I mean, this beam will be split into two parts, and it will go there, here, and this beam will also be split, and it will also go here and here. So here we'll have two beams at least, and we have to count how many times will we have in general. The first part is being solved without any dynamic programming. It's just a tail recursion. We just count splitters. Every time when we encounter a splitter, we will just add it to this number. For the second part, we need a bit of dynamic programming, which I also implemented with tail recursion, but you can implement it any other way too. I will just count on every step how many beams I have, and on the next step I will multiply it twice if we split it, if we have split it. Let's look at the visualization, because again, this is the part I love the most about this task. Let me copy my real input, because the test one is quite boring, and paste it here. Here it's huge, as you can see, and we can run it, and we'll have this nice scan line in which we can zoom and so on. And we see that it was hard to foresee, but for example, in this point there are 5,000 beams. In this point I can't even count, it's millions of beams. And in this point it's probably billions of beams. And the whole thing looks like a nice Christmas tree, which I actually like. And these splitters will be just toys on our tree. Day 8 is already slightly more challenging than the previous ones. For day 8 we have a number of 3D points, and we have to connect these points together. We should find shortest distances between them and connect the shortest ones. And when we do it, after we do it, for the first part, we should count what is the length of all the shortest circuits we have. For example, first part is being solved very, very straightforward. I have just a list of sets. Here, list of sets of 0.3. 0.3 is my own class, which is essentially just X, Y, and Z. And every time when I find all the distance, I find all the distances between every pair of points, sort them by their length, here, sorted by distance, and I take as many as I need. And then I will just connect them into circuits. When two circuits connect, I will remove one of the circuits from my list. It will become one huge set. And this is essentially all. And the thing is, part 1 is not different from part 2. It's just for part 1, I had to connect only 1,000 first closest points. For the part 2, I had to wait until all the points are connected to the circuit. What I like here, again, is mostly a visualization, because algorithm is, again, pretty much straightforward. For the test input, let's just reduce this number to 10 and look at how the algorithm finds the shortest distance. And here we have it. Here we connected 10 closest points. And we have 4 active chains, and result for the test input in my case will be 40. And I won't show you how it works on a bigger input because it takes quite some time, but that's essentially all. Day 9 begins simple but continues very, very hard. At least I wasn't able to solve it without external dependencies, which is already a sign of something being hard. So the thing is, we are provided with a set of coordinates of points in 2-dimensional space, like this. And for the first part, we have just to find 2 points which are the angles of the biggest possible rectangle. Solution for this is obviously very simple. We just combine all possible pairs of points. We calculate the area, which is just one side of rectangle multiplied by another side of rectangle, and we find the maximal area, and we find it. However, the second part is much more tricky. Now, the thing is, all these points create a polygon, which is pretty big, and we have to find the maximal rectangle which fits inside this polygon. There are multiple ways to approach it. So the way I did it, again, I built my polygon, but the way I did it, I used Java Polygon, which gives me all the possible values or all the possible functions to work with polygons. I provided it with x coordinates of my points, y coordinates of my points, and number of points. And then to find the biggest rectangle, I again combine all the possible areas of rectangles, 2 pair of these rectangles. Then I sort these areas descending, and then I will find the first rectangle which polygon contains. And luckily I have this polygon contains inside Java AWT, because when you look into it, the implementation is not crazy complex, but it's hard to write when you don't know how to write it. And then I'm looking for the first biggest rectangle. I like the visualization here again. Let me show you. Let's open our default and do something like this. Load points. As you can see, this is a huge, almost circle, and there is a huge part missing. When we will write, this is how we check all the best possible rectangles. It takes quite some time actually. I'm not sure if we'll have enough time. Let me speed it up for you. So here we found the biggest rectangle. Now we should find the biggest rectangle which fits inside this. And we see that it lies on one of these polygon's internal sides, which is again some amount of code. And when we just visualize it slowly, we see that it takes time to solve. We are just lucky that Java.AWT package contains everything needed to work with polygons. But Gemini was able to solve this thing for me in, 500 lines of code, which is not that much actually. The day 10 was actually so hard that I spent almost a whole day solving it. The idea is very simple. The implementation and to understand how to implement it is very hard. So the idea is the following. We have several lights. All of them are switched off by the default, and we have several buttons. Every button will switch state of every light. For example, this button will switch the state of light 3. This button will switch the state of light 1 and 3. This one will switch state of 0 and 2. And our goal is to find a combination of buttons that will enable only lights indicated as hash. So for example, here 1 and 2 should be enabled. The implementation for the first part also took me some time, but I figured it out. So we have to count how many possible combinations of button presses are there, and then we should XOR an amount of buttons we used, but I didn't use XOR. I don't like bitwise operations, so I created a list of switches, and then I check on every possible combinations. I check if my current state equals my target state, and if yes, then I say that, hey, here is the correct combination of buttons. I know it takes some time to understand. The code is not trivial, and even here I have to store current state with button list, with a button on every button in my combination. But it is possible. The second part, though, is much trickier. In the second part, we have to understand. So here, this button will increment number 3 by 1. This button will increment numbers 1 and 3 by 1. And we have to calculate how many times we should press each button to achieve the desired state. And obviously there are many ways to achieve it, but we need to find the minimal amount of buttons pressed. And this part I couldn't figure out how to solve. I know about Gaussian elimination, but here it's not enough because, for example, let's look at the whole thing as a linear algebra problem. So we have to press A times this button, B times this button, C times this button, and we should get the numbers n, for example, m and k. If we think about it, we have more variables than we have equations, because we only have like 5 lights, but we have, for example, which are variables, 3 equations, which is a problem. There are solvers for this task, and I discovered one, and it costed me many hours actually, which is called ojAlgo, which has been written like this, ojAlgo. So here I say that I'm creating an expression-based model, which is created to solve problems of linear algebra. And I'm saying that, hey, I will have this max value, and max value is obviously, for example, in this case, it will be 7 multiplied by 3. It's impossible that to achieve the goal of all of these things, I need to press more buttons than 7 multiplied by number of lights. Then I will create coefficients of variables. It will be just button with its index, and obviously max value of it will be what I just told. It's impossible that I need to press any button more than 7 times. Then I will create a system of expressions. So I will create an expression, and its maximal and minimal value will be target counter state, which is essentially 7 or 4 or 5 or 3 in this case. And for every variable, I will add an expression with coefficient 1, which will create a system of expressions looking like something like this: x plus y plus z equals 7, and then a plus b plus n equals 5. Or maybe we have x here, just for them to understand. And then I'm saying that I also have an expression called total, and lower and upper value of this total. Lower is just how many buttons, what's the maximal value in my number buttons, and upper is this max value multiplied by button size. Here I also have to say that for each coefficient I declared here, in my total its weight will be 1.0. It means that it's not 2a, it is exactly a. And I want model to minimize value of my expression. And then I will sum for every line in my input. I will sum it. Let's run it. So on my machine, it takes 100 milliseconds to solve. But again, this is not a code I wrote, so I am not kind of proud of it. But what I'm proud of, I learned a new library. And again, the whole advent of code thing is about learning for me. It's not about solving puzzles itself. It's about learning, and I learned something new today. Actually, it took so much time that I didn't even have time to create a visualization for it, so we'll skip this part. Day 11 is again pretty straightforward, especially if you know what you're doing. We have this graph where from node AA you can go to nodes U and HHH, and from node GGG you can go to the node out. And for the first part, we should just count how many ways do we have from the node U to node out. How do we solve it? It will be something like this. I use a library called JGraphT, which allows me to create a simple directed graph. I add all my vertices there, and then I create all the edges there. And then I'm saying get all paths from U to out. I'm interested only in simple paths, and I don't care about the maximal path lengths. And for the first part, it obviously works. But for the second part, we have to find all the ways from SRV to out, and we are interested only the paths that go through FFT and DAC at the same time, without any particular order. So there is no algorithm in JGraphT to count all possible paths, but what we can do is we'll sort all our vertices in topological order. Then we'll find which of them is first. It's either DAC or FFT. We know this because it's a cyclic graph, luckily, because otherwise it would be impossible to count all the possible ways from one point to another. Then, so if it's first DAC, then FFT, then we count amount of paths from SVR to DAC, then from DAC to FFT, and then from FFT to out. Otherwise, we'll find all paths from SVR to FFT, then from FFT to DAC, and then from DAC to out. But the amount of paths will be so huge, it's impossible to just call get all paths. We'll have to come out with our own solution. But it's again pretty much straightforward thing. Like in our day 7, we can just create a map of paths from one point to another and just return number of paths to our target, or otherwise 0. The thing itself is not too impressive. Let's look at the visualization. Oops. Day 11 HTML. We'll open our default browser. Let's also open my input.txt. Here we go. Let's quickly load this data. You can see that actually the graph is pretty impressive. And for the first part, U is located here and out is located here. And when we run it, we see this nice dots that say, hey, there is 649 paths. For the second part though, it's slightly more interesting. We'll have to run it multiple times, the same algorithm, to find all possible paths. And here you can see very simple visualization of our nodes in topological order. And what I like about this visualization, again generated, it's very, very dynamic. We can see how it spreads over the network. It will make several paths because we call it several times. I could cache it, but it won't save me too much time because actually the algorithm is very, very fast. And at the end, we'll see the end result. I won't wait for it here, but you can just trust me probably, or we can probably run it again on the high speed. I'm not sure how fast it will be. We won't wait. And now to day 12. Let's open it. This is the day I kinda hated. We have description of shapes, index descriptions of shapes like this. And we have these definitions of grids. For example, this grid is 4x4, and it should include 2 shapes of type 4. And this is 12x5, and it should include 1 shape of type 0, 1 shape of type 3, or 2, sorry, 3 shapes of type 4, and 5 shapes of 2 shapes of type 5. And I actually wrote a pretty much complicated solution for this problem, which actually tries every possible position for every possible shape with backtracking. But it turned out that for actual shape, that for the actual input, we don't need it. For the actual input, but I left my solution here so you could check it out on my GitHub. But for the actual input, we can just count the total area of all the shapes we should place there, and if it's less than the size of the grid, then it will go there, otherwise it won't. But let's try to run my solution and see how much time it takes. It takes some time to compile, obviously. Yeah, so the result is 521 and it's 700 milliseconds. But again, for the first part, they didn't tell us that there won't be tricky situations. So I had to write this whole bunch of code with normalization, with rotations, with all kinds of stuff, with even parsing here is pretty long. And all the logic is can fit is actually also long. And this is the main function, DFS, depth first search, which tries to do backtracking, but it never happens on an actual input, which is just sad. I mean, I spent a couple of hours on it, and I probably could spend like 10 minutes on it just parsing the input, and that's all. Anyways, I'm thankful to Eric Wassel, who creates these tasks for us every year. It was a lot of fun. Even the last day, it was a lot of thinking and experimentation until I found the right answer. I'm happy that Google helped me with these visualizations, even though they make everything more enjoyable and visual. And if you are like me, please participate in Advent of Code. Please ask questions. Please find solutions. Please learn new things. At this point, if you like the video, subscribe to our channel. If you want to comment, leave a comment below, and see you the next time. Pass out.